Hello and welcome to our webinar, The Tech You Need to Supercharge Critical Banking Apps. My name is Samantha Kelly and I'll be moderating today's webinar. I'm joined here by Boris Bolnov, the VP of Technology here at NuoDB. In this webinar, Boris will discuss how you can overcome cost and technology challenges of moving to the cloud using Google Cloud Platform powered by Intel Optane DC persistent memory and NuoDB's distributed SQL database. Before we begin today's presentation, I'd like to review a few logistics. Our webinar will last about 45 minutes with 15 minutes for Q&A at the end. The webinar will be recorded and the video and slides will be made available for replay. Attendees will be muted during the call. However, you may submit questions at any time during the presentation using the questions panel in the control panel. So with that, I'll turn it over to Boris.
Thank you very much, Sam, and thank you everybody for dialing in. We're going to have exciting 45 minutes ahead of us. So the topic of the presentation is really how do we create large OLTP systems in the cloud, and why would we do that? And even though the content primarily targets banking industry, the technology and approaches themselves are very horizontal. So if you're not from the banking space, don't worry about that, but we'll try to use as examples, and most of our immediate experience and targeting is really around banking. So what we'll do is in terms of the agenda, we'll talk a little bit about the context and why what we're talking about is relevant to the industry. Then we'll talk a little bit about the individual companies and technologies. Clearly, everybody knows about Google and Intel, but we'll talk specifically what do they bring to the table, if you will, in this particular use case, and how it all aligns to deliver certain capabilities, which otherwise are pretty challenging. So then we'll talk and actually show a sample application that has been built together as a joint development exercise between three companies, Google, Intel, and NuoDB. And we'll explore how the system works. So all the concepts that we're going to be talking about are actually going to materialize in an actual application. So that hopefully we'll have a little bit more, provide a little bit more insight for everybody than just talking about concepts. So with that, as Sam said, my name is Boris Bolnov. I'm from NuoDB. On this both presentation and the application development, as I said, multiple people have been involved from Intel and Google. They're not here with us today, but I definitely want to credit their contribution to this effort. And with that, let's jump right in. So most of us, or all of us, are the users in one shape or form of banking services, and probably most of you on the phone are keenly aware of the fact that there is a fundamental transition that has taken place where, in general, bricks and mortar companies are rushing towards digitization, but specifically so in the banking industry, there is a very well-defined and embraced trend of something that banks refer to as digital transformation, and that is the process of converting traditional on-premises systems to cloud environments, right? This is the trend that is that sort of in a different level of maturity across the globe. We happen to be engaged with companies across the globe, and clearly the Asian companies are a little bit ahead of everybody, embracing the public cloud infrastructure for this type of applications. Things are going a little bit slower in Europe and US and Latin America, but the trend is absolutely clear, and it's really the question of not if it's going to happen, but when it's going to happen. When will the systems that run banking today actually are moved to the cloud environment? And by the way, it's important to notice the reason why this is so important. The reason banks are moving towards public infrastructure, cloud infrastructure, is so they can rationalize their systems and at the end deliver better user experience to their customers, right? Now the touch points are very different than they were 5-10 years ago. And also those systems can evolve much faster. So the new functionality, new capabilities related to user experience and functionality can be developed faster. As most of you know, that traditional infrastructure is very slow in terms of being updated and delivering new capabilities. So therefore this picture, right? And the question is then, and by the way, another important point to note, that everything that we're going to be talking about is applicable not only to the cloud infrastructure, but also can be used and exercised on premises, right? So this technology stack, this technology that we're going to be talking about, can reside on premises, in private cloud, or in public cloud. And therefore, really organizations which are looking forward to this transition to the cloud eventually may start and are starting this kind of development for their internal applications. And therefore, the overall sort of umbrella topic, if you will, for this discussion is not necessarily just how do you move and create these large systems in the cloud, but how do you get ready with cloud-ready architecture in whatever state you are in terms of moving to the public cloud infrastructure. So the next interesting topic, just again for context to touch on, this transformation from traditional approaches to new cloud approaches involves all aspects of organizations, right? And generally people refer to this as people, processes, and technologies, right? And what this means is that everything is changing from the type of infrastructure applications are running to kinds of experience people have to deal with software construction and operation. It deals with processes, how software is developed. And it also deals with a variety of different application architecture approaches that are emerging, which are dramatically different from what everybody's used to having on premises and traditional architecture. One element which is really not well understood or recognized by a lot of companies and individuals who are new to this process is the fact that just like everything else, databases have to undergo a fundamental transition and transformation, if you will. And that's why you see here on the bottom that in terms of the database technology, databases which are adapted to the cloud native infrastructure have to be distributed in their nature. So if we look at that stack, if you will, of different types of activities and technologies that need to be transformed, on the very right side, you can see company logos. Within the context of this particular presentation, we'll talk about Intel, who is providing new types of infrastructure hardware, which enables this scale in commodity environments. We'll talk about Google, and Google brings unparalleled experience in terms of their ability to build massively scalable distributed systems. And lastly, NuoDB is a technology which is specifically suited and built for purpose for taking advantage of commodity in a way that is essential for building mission critical applications. We'll talk why that is the case. So that is a quick background on sort of players, if you will, that will be contributing to this overall architecture and overall example of how to build the large systems in the cloud. Before we go further, though, another point of sort of clarification and focus, which is quite important to frame the discussion that we're going to have, is really understand, first of all, what are the systems that we're talking about, right? And here on the right, you see examples. If you're a bank, you'll have a range of applications that vary from, human resources and conference room scheduling on one end of the spectrum to something that really runs the business. And that would be the systems which include core banking, credit card payments, processing, risk and compliance, variety of different types of disciplines which are really driven by or powered by a set of applications which are referred to like core applications, right? And that's what we're talking about here. We're not talking about the less critical application. We're talking about the most critical applications. And really the question, how do you move those applications and systems to the architecture which is cloud native, right? Then on the left side, we have a couple of other important considerations. It's not just a question of moving systems to the cloud architecture and being able to execute in the cloud. It also, with this transition, what is very important to appreciate and understand is the fact that with this transition, systems become larger. And there are a couple of reasons for that. The first reason, to begin with, the systems that these types of systems that exist today, generally based on very well understood and reliable technologies such as Exadata, Oracle RAC, or mainframe with technologies like DB2. So these are the types of systems which exist today, and they're very large to begin with, right? And those are the systems that have to be moved. As they move, as being moved to the cloud, they also need to be aggregated and consolidated, right? So today, if you have an inside knowledge about how banks operate, generally a bank would have 3 to 5 to 10 examples of every systems running based on different types of acquisitions and moments in history and so forth. So as a clear intent for moving towards public cloud or cloud architecture in general, the systems need to be consolidated. What this means is that either within a particular domain, such as banking or cards, or cross-domain, like taking all the transactions for the customers together, the systems become larger and larger and larger. Therefore, scale is very important. Also, what architects are considering is the fact that this new type of architecture needs to be able to sustain them for the next 5, 10, 20 years, right? So it's absolutely essential to have enough headroom for the systems to grow and become larger and larger. And therefore, these topics that we're exploring today are twofold. It's, first of all, is how do we move the systems which exist on very reliable, very trusted infrastructure on premises today, how do we move it to the cloud and not only retain the same SLAs in terms of continuous availability, in terms of ability to scale out, and other aspects of their behavior today on premises. How do we capture the same kind of characteristics in the cloud, in a software-only environment? And by the way, the system's got to be larger and larger and larger. So this headroom for future growth is essential. So that's a backdrop for what we're talking about. Now let me switch gears a little bit and talk about the companies and why this sort of reasonably random combination of companies like Google, Intel, and NuoDB, why each one of those companies brings an integral part of enabling to the table. So first of all, Google clearly doesn't need the introduction. As I said before, Google pretty much invented the whole space of massively distributed computing, right? As you remember, 20 years ago, they've introduced the search as their first capability, which rapidly grew and became incredibly powerful. But interestingly enough, today, Google operates, and I just learned the statistics as I was working with my colleagues, that today Google operates 7 properties, internet properties, each one of them having more than 1 billion users, right? So if you imagine the scale of this kind of operation, it's really staggering. The underlying infrastructure underneath all of those properties is shared. It's a platform. And interestingly enough, Google Cloud Platform is based on the same kind of best practices and technologies that allow Google to operate those other properties like YouTube and Google Maps and others, Gmail, effectively. And the basic characteristics, for those of you who are technical, are based, as you know, on containers and data streaming. But it's really the knowledge of how do you put all of these components together and operate them at scale to deliver this remarkable performance is what Google's experience is. So interestingly enough, we're working with a number of cloud providers. Google's strategy is somewhat unique in the sense that not only they provide the cloud platform and certain technologies, but also they have a team of people who specifically tasked with transferring the technology of how to build large-scale distributed systems in the public cloud or on premises with their tools and their lessons learned. And that's a very powerful sort of strategy that allows them to work very effectively with the largest of the enterprises in banking specifically, but across other industries as well, and to deliver not just this knowledge, but translate that knowledge into large systems in the cloud, which are mission critical, core systems as we talked about. And they are really one of the drivers behind these initiatives. So Google brings a lot clearly to the table in this particular context. The second company, which also doesn't need the introduction, is Intel. So Intel came up with technology which is called non-volatile memory. That's a generalized technology description, if you will. But if this is translated into the specifics, Intel developed new type of memory which sits next to their CPU, which is a core processing unit infrastructure, and allows very fast access to that non-volatile memory. And that non-volatile memory can be configured in two ways. It could be configured just as additional memory. So if you used to have, just as an example, 100 gigabytes of memory in a machine, you can configure the same machine to have 10, 20 terabytes of memory. So imagine this jump from gigabytes to terabytes, where memory becomes abundant, and the whole architecture sort of switches from being storage-centric, where memory is scarce and storage is available, to something being memory-centric, and the design is really governed by how much memory you have available and where you access this memory and how fast that access is. So as I said, that non-volatile memory can be configured as memory, or it can be configured as storage device. And storage, as a storage device, that technology achieves, again, remarkable improvements in terms of how fast the data can be persisted, right? And because it's non-volatile, essentially what this means, if the power is taken away, the data remains. So you can bring the power back and the data will still be there, just like storage technology that we have today. So this technology group, if you will, or product, referred by Intel as Optane. They refer to it as Optane Data Center Persistent Memory Module. And this is truly disruptive technology. It's been in development for 10 years, just been brought to market last year, and already has been very successful. But for those of us who sort of like track the technology, this is truly the first development of improvements, fundamental improvements in memory infrastructure in the past 25 years, which is, again, quite remarkable. What this technology allows architects to do is to address systems which are massively larger and more scalable than the ones which exist today. And therefore, as we'll see in this example, as we move forward, Optane memory from Intel really underlies this capability of how do we build very large systems with massive future scale in environments which are largely commodity environment, meaning that the only way we can access all these resources is through virtualization and software. So very, very exciting. And lastly, the last company in this triad, if you will, is NuoDB. And NuoDB is a distributed database. It has a lot of different interesting characteristics. For the purpose of this discussion, two are important. First of all, it's memory-centric database, meaning that the data resides in memory of database processes, right? And therefore, you can probably already connect the dots that given that it's a memory-centric database, given that Intel Optane memory provides vast amounts of available memory, this combination's got to be very good. And it is a very good combination indeed. The second very important aspect of NuoDB, critically relevant to what we're talking about, is the fact that NuoDB is highly resilient, right? We refer to this as continuous high availability, meaning that as certain components within the NuoDB database fail, the database service continues to be delivered. Right? And that is essential characteristic. We'll see that this is foundational how you build this type of mission critical systems, and therefore NuoDB sort of like brings all the capabilities underneath of Google distributed systems, of Intel Optane memory, and how do you tie it all together? NuoDB is that software piece which happens to tie it all together. Okay. So a little bit more context setting, and then we'll jump into the actual application to illustrate the concepts. But if we take a broader look of what are the types of technologies that are available in public cloud versus the ones which are built on-prem, you can see that from this quick high-level description that there are multiple relationships exist for how you transfer technology from one domain to another. If you have big data infrastructure like Hadoop or on-prem, you move it generally to technology called Bigtable in Google space, in Google Cloud. If you have analytics, there is a facility which is called BigQuery, which allows you to process billions of records in real time. And then we get to what sometimes people refer as operational systems, right? And we introduced a concept here, a concept of this kind of application tiering, if you will. And I mentioned it in the beginning. Generally, in an enterprise, in a bank, you would have systems which serve different purposes. Some of them are more important than another. So normally, banks describe them as a category 0 to category 5, or tier 1 to tier 5, and so forth. But essentially what this means is tier 0 are the most critical applications, and then you go to all other applications which may be less important. So in the context of tier 0 applications, which are, as we said, are the most important ones, there are several possibilities in terms of technology for online transaction processing that can be used. And specifically in the case of Google Cloud, there is a distributed database, native distributed database that Google provides called Spanner, right? An alternative to that is a combination of technology that we're talking about here, which is a combination of NuoDB, Optane, and Google infrastructure for building applications being used as an alternative stack, if you will, for building the apps. It's probably a longer discussion, but let me just mention that Spanner and NuoDB, in terms of what they do and how they do it, is dramatically different, and generally two do not coexist in a span of a single domain of a single application. It's pretty clear as you encountered on this kind of decision what is the right technology to use. Specifically, what NuoDB is used for today is moving, as I said, mission critical transaction processing applications. Today, those are generally housed by three technologies. It's Exadata, it's Oracle RAC, and it's IBM mainframe with DB2. Those are the technologies as they need to be reframed and rethought as they move towards the cloud architecture. That's what NuoDB does, right? Effectively, what today those kind of infrastructures provide through the combination of software and hardware on premises, NuoDB is able to accomplish just in software in a cloud environment and deliver the same kind of SLAs, the same kind of performance, the same kind of reliability. So with that, let's jump towards describing the application, and on a very high level, and we'll recite it a few times, what's important as you're building those large transaction processing applications in the cloud architecture is three foundational characteristics, if you will. First of all, performance is very important. Why performance is important is because as you re-architect the systems, as you move them from one environment to another, the expectations of performance from banking users is at least the same, if not higher, right? So this generally is materialized in a form of, if you ask a bank for a money transfer or you want to have a balance inquiry, how fast does the bank react, right? As a consumer, as a user, that's what you see. So you shouldn't care whether the infrastructure actually resides in the public cloud or on premises. You always have to get the same kind of response in terms of time. Also for the banks, it's important how many users can the bank service simultaneously, right? Normally those are thousands and thousands of users, and that is managed, embodied in a performance characteristic called transactions per second. That translates into how many users can you service at once. The second very important characteristic is a scale, right? So scale, as we said, traditional systems are large for these types of applications, but they're not large enough. They're going to become much larger. As a matter of fact, we're dealing with a number of Asian banks which are orders of magnitude larger today than their European and American counterparts, and the expectations of the future scale are even larger than that. So scale is critically important, and scale generally translates into how many customers can you service, right? Is it a few million, is it tens of millions, or it's billions, right? And that's where the scale comes in. And lastly, what is the third foundational characteristic is resilience, right? Because whatever happens, the machine can fail, software can fail, the data center can fail, or availability zone in the cloud. The system needs to continue to operate, right? You'd expect that whenever you come to get a knowledge of where your money is, or somehow somehow have an operation relative to the money in the bank, that it happens, right? The bank is always available. There's always a dial tone. So resilience is critically important. So let me describe this simple application. We call it a cloud bank or model bank. And here's sort of like a quick diagram, if you will, a conceptual diagram. Interestingly enough, and again, most of you are professionals in the space, and it's common knowledge, but all of those transaction processing systems are generally very similar. They have a set of data which is continuously updated, and that's the data about accounts and customers, portfolios, cards. That's where majority of immediate operational information is stored and updated. And then there is a second element to the systems like that, which deals with business transactions or storing what is called monetary transactions. And that may be transactions around core banking where you deposit and withdraw money. It could be credit cards where you're paying for something. It could be loans where you're making daily or weekly or monthly payments. All of these are monetary transactions, and those have to be captured and kept around for a very long time. Also, that long tail of business transactions or monetary transactions can be used for a variety of different purposes. They can be used for fraudulent activity detection, right? And then those systems have to go back and analyze all kinds of operations a particular customer or combination of customers have done for a number of years. It can be used for customer service or a variety of other purposes, but ability to access that long tail of data is very critical. So that's the foundation of our system. You can see two vertical bars representing the notion of this is our customer data, right? That's operational database. And then there are a number of horizontal bars which represent the transactions. So an interesting thing in what we wanted to do in this particular application is show how size matters, and we can make this a much larger system that people normally used to. So in this case, if banks today, even the larger banks, are operating in the order of accounts being 5, 10, 20, 30 million accounts are the large banks. What we're doing here in this system, we're modeling not 50 million customers or accounts, but we're modeling 1 billion. So clearly that is a much larger number. It's a much larger system. And as you'll see, we'll be updating it in real time. We'll be able to get a sense for how the performance is. Quick note that clearly this is not a truly a banking system, and it's much lighter weight and it operates faster at this point in time. But the goal here is to just demonstrate that this kind of numbers are achievable. And as you put more business logic into the systems, the system should still continue to operate very, very fast, right, and retain the same kind of performance. So again, two numbers to monitor here is 1 billion for accounts, and then just so we are representing something at scale, we also populated the system with 20 billion transactions, business transactions, and therefore these are the kinds of numbers we'll be working with in the next few minutes. The next slide, this slide demonstrates the physical architecture of the system we're going to be monitoring and observing in terms of the hosts and where the database servers are deployed. So you can see the two boxes on the left side representing the Google Compute engines, which have 6 terabytes of Optane memory configured with them. So you can see the left box on the left and the box on the bottom being this house, and they house database servers. And then on the right side, we have a much smaller host, which is 200 gigabytes inside with traditional memory. And it hosts a much smaller or houses a much smaller database server, which only has enough memory to of 100 gigabytes to service much smaller loads. But the idea here, we have a distributed database, and we'll want to measure 3 things. First of all, we want to measure we want to see the scale. We want to see all these records being there, and we can still operate in the system. That's important. We'll also want to compare performance, because performance in the cloud with Optane should be similar to that of traditional memory. So it's very important for us to have these two types of memory running next to each other side by side so we can observe it. And lastly, you can see that this is really underlying application is a distributed database which enables the performance. It enables different kinds of workloads being executed together. And most importantly, we'll see it later on, it enables resilience. So if some of the servers go away, the database service will still continue to operate. So what we'll do is I'll switch now to a video of the system, and we'll walk through the different type of operations of that system. So forgive me for the quick glitch in sleight of hand. Here we go, different screen. So now we're running the video of the demo, and you see again, I'm just restating the same three most important characteristics that systems should have today. And the way we organize the demo, generally for those of you who are in the back-end infrastructure space, you know that databases and transactions are pretty boring. You normally don't see anything. So what we've done, we've taken all of these important characteristics that we're monitoring and we put them together on a dashboard, right? So I'll explain all the different gadgets that appear here, but just the high-level observations, what you see here is a live system which is populated with data. You can see now that in this system, and we'll demonstrate that, we'll actually drill in and see, but we have 1 billion accounts, and we have more than 20 billion transactions, and this system is operating in Google Cloud, and underneath that is all Intel, Optane, and NuoDB. So as you can see on the right side of this dashboard, you can see that the business transactions are actually flowing here, right? So if you look at the characteristic bank, you have operations which are very common, which is deposit, withdrawal, data transfer, and inquiry. And those are the operations that we're running through the system. We'll also see here a gadget which shows us performance. You can see TPS and you can see latency. And we'll see how that relates to our infrastructure. And also you see historical view. And the important point here is that you can see that system is able to deliver very low latencies, right? In fractions of a millisecond. And for different applications, this means different kind of latency and performance, but nevertheless, it's in a very low numbers, and therefore it means that the system is very responsive. So now we're going to drop behind the dashboard, and this is actually SQL shell, which developers and administrators use all the time. And the first thing we're going to do, we're going to validate, and that's what we're going to do here, the numbers that we've claimed the system has, and we can see here that we have close to 22 billion transactions now because the system has been running for a while, and we have billion accounts. Now what we're going to do, we're going to actually look at the data to just make sure that the data behind the demo and application looks real. Now we've asked, give us all accounts for a particular customer. You can see customer ID is 12345. We see number of accounts. We now can say, tell me all the operations that this particular customer has done in a certain period of time. And you can see transactions. You can see that we have different types of transactions. We have deposits. We have transfers. Transfers move data from one account to another. We update balances. So this system performs just as any core banking system would, right? And we can observe this over the period of time. So that's the data within the demo. And as you can see, the system is operating. We see two gauges in front of us. On the left gauge, we see performance of the Optane memory, and on the right side, we see performance of the traditional memory. And you can see that they are quite comparable. Now, a little bit more graphics. The left server hosts a number of applications and databases, and you can see that the left gauge shows us performance of Optane. The right gauge shows us performance of traditional memory. And the important point, as I said already, that the performance is similar, and that's what we would like to see, right? We're basically saying that the performance of system in the cloud with Optane is similar to the performance of traditional memory on premises or in the cloud as well. So that is the exact characteristic we're looking for. But here, this slide, we're really getting down to what's the secret sauce of this whole architecture, and that's the Optane memory. So it's not just important what performance you have, but what's the most important observation characteristic is, can you maintain the same level of performance, which is TPS and latency, over very large amounts of data? And that's exactly what Optane delivers. So if you can see the larger bubble here, which represents the Optane memory with a certain number of records in there, that service can support 1 billion records with indexes and all other underlying infrastructure. On the right side, where you have a smaller bubble, we can only support 300,000 customers, which is the difference. So the most important point is the same level of performance on much larger data sets. Now we're going to switch gears a little bit. We're again looking at the console, right? What's happening behind the scenes, and we're going to demonstrate that not only the system is performant at scale, but it also is resilient. So what we're seeing now displayed is that the database has 4 servers. We can see those in the picture, but also you can see those in the console. This is the state of the database. And what we're going to do now is something that generally operators don't want to see or do, right? We're going to kill one of the servers. And you can see that on the right side, the little red cross appeared. The server went away, right? So the database now is smaller. It doesn't have all the servers. But what's remarkable, you can see that the write gauge has 0 transactions going through it. It's dead, right? And we can see that the history shows a drop in transactional throughput. But the system is still alive, right? You can see that the left gauge is up and running. We're still processing transactions. In the right upper corner, money is still deposited. Inquiries are still made. This means that the system is operational even though one of the servers went down, and that is resilience. That is the most important, one of the most important underpinning characteristics of the whole system. Now we're going to do something a little bit different. In a distributed system, it's not only important for the system to survive failures like the one we just observed, but it also is very important to be able to repair itself. Okay? Self-healing is a very important characteristic of a distributed system. So what we're going to do now, we're going to start another server, and that's exactly what we just did. The server came up. You can see that the system gave us back a thumbs up. We can see that now we have 4 servers running. The little green arrow appeared on the right side. And what's important, you can start seeing gauge on the right side in the dashboard coming to life, right? And that is an example of system self-healing or recovery by just us restarting the engine. We suddenly on the right side see that the system that was dead in a prior minute is coming back to life, and you can see that its performance is increasing as it collects more and more data, and effectively the system heals itself and continues to operate. So again, scale, speed/performance, and resilience are the most important characteristics of a system like that, large distributed transactional processing system. So let me switch back and let me share with you the final thought here. And the final thought is just summarizing what we've just saw. So the goal, the objective is pretty clear. And it's undisputable that that's where everybody in the industry understands that's where everybody's going to end up sooner or later, right? And that's the cloud. An interesting characteristic you see, like bank as a phone here, a little icon, but that's truly how dramatically the whole banking industry is shifting from bricks and mortar and retail branches to something that is really, customer centric, where the online devices is your view of the bank. And in order to do that, the banks have to be able to be agile, reliable, and fully digital. And that is a transition that is happening. So clearly, those systems are very large. Those systems will exist in commodity infrastructure. They cannot rely on very large hardware anymore, no exadatas or mainframes in the next life. And that is what digital transformation is. Hopefully, we've been able to communicate the message here is that there are ways of getting to this types of scale and this type of characteristics like resilience and performance in a cloud today. That's what we're working with a lot of customers on, larger banks, smaller banks, tiny banks. And on the left side of the slide, you see the combination of the 3 companies, which we do a lot of joint development, as I mentioned. We do a lot of innovation and aligning and optimization across those boundaries. But Google, Intel, and NoGB are those foundational components which allow you to be sort of like ahead of the curve, if you will. This is not an easy journey. And in a journey like this, it's always important to be guided by somebody who knows what to do. So even the first project that you encounter on is a step in the right direction. It succeeds and it paves the way for the future innovation, the future benefits. So at this point in time, I will stop and we'll look if we have any questions. I urge you to, if you have questions, to type those in, and we'll try to answer them. And if not, we'll follow up on the email but we'll make sure that all the questions and your interest is sufficiently serviced.
Awesome. Thank you, Boris. Very interesting information and an awesome demo. Thanks for sharing. We do have a few questions for you from the audience.
Okay, great.
So we can get started with the first one. Do you think large banks are ready to move fully to the cloud, and does this technology change that shift?
Okay, great question. We hear similar questions quite often. So the question is whether banks are ready. I think everybody at this point understands that things need to dramatically change. Different parts of the globe have different regulatory requirements and limitations which allow or encourage them to move in this direction. But it's clear that there's a sufficient amount of technologies that exist today that you don't have to physically move to the cloud, public cloud, but you can start developing and enhancing and re-architecting your systems for the cloud architectures while you developing the systems on premises, right? And that technology varies from, it is based on containers, it is based on technologies like Kubernetes. Google provides something called Anthos, which is platform-independent set of enterprise container capabilities, which can be used on premises as a hybrid or on each individual cloud. So a lot of technologies come together. Clearly, for the very large systems, like the one we've described here, generally that address core banking functionality, technology like Optane is essential because that's what allows you to create a scale, right, and scale in the future to very large systems. And NuoDB is the right technology for the same with the same point that it's important to take advantage of commodity computing of a lot of memory, but at the same time ability to have inherent resilience in a software cloud environment is essential. That's what NoGB delivers. So the quick question is yes, people are ready, technology is there. It really is specific to the regions of the world where how quickly can people go there.
Awesome. The next question is, can't I accomplish the cloud migration with my existing RDBMS? What does NuoDB offer that a SQL Server, IBM, or Oracle does not? Okay.
Also reasonably common question. So the question, can you accomplish it? The first glance is absolutely, right? You can just what is called lift and shift. So you take the systems you have on premises today, you run them in a cloud, and you're done, right? There are two aspects of it. First of all is the cloud allows and brings to users users of the cloud unique capability that you consume resources on demand, right? And that's what makes the cloud to be, on one hand, very efficient. You don't have to over provision what you use, but on the second hand, you can scale as you need as your demands grow. So traditional technology, database technology, doesn't allow you to do that, right? You essentially have a single server which can become larger. It rarely becomes smaller, but you cannot scale out with this type of technologies. And that's one of the reasons why, in order to address very large scalable systems on premises, it's not just Oracle, it's not just DB2, but it's a combination of software and hardware, which is brought together to guarantee, first of all, continuous high availability, right? So if something happens with a database, the hardware will fail over or make sure that the systems are still operating. But secondly, scale out, right? So scale out as multiple servers, or in the case of mainframe, the mechanism is quite a bit different, but nevertheless, you can add hardware capacity, and that increases your software capacity or system capacity. None of this exists in the cloud, right? So in the cloud, if you have a traditional database, then you use traditional techniques for high availability, such as standby instances and so forth. You'll always have the period of time in which system fails over, right, and therefore not available. And for systems as the ones we're talking about, that kind of failover time is just simply unacceptable. So to answer the question that came online, the simple answer is you can fake that the system executes in the cloud as well as it does in Exadata or mainframe, but in reality, it will never have the same SLAs. NuoDB has been specifically designed to address, aside from other characteristics, but this continuous high availability and scale out are the basic characteristics of NoGB, and it's accomplished purely in the software. And therefore, that is the right tool for accomplishing these types of tasks in the cloud.
Okay. The next question is, when using GCP and Optane, why would NuoDB be a better fit than Google's own Spanner?
Much more difficult question, but let me try to address it to the best of my knowledge. So Spanner, for those of you who know this technology, is a very mature database, been used by Google for many, many years for their internal tasks, such as manage advertisement across the globe. It's based on incredibly expensive infrastructure that Google built, and then effectively it's another example of combination of software and hardware that delivers remarkable performance. But couple of observations on that. First of all, it's very expensive because it utilizes the hardware. It's not transportable, so if you use it with Google, then you're pretty much stuck with Google Spanner. That's the second one. But lastly, it solves certain class of problems phenomenally well, meaning that if you have to run transactions across the globe at the same time, this is probably the only technology which can achieve the kinds of characteristics you would be looking for. What we're talking about here is a very different class of applications, which is transferring the existing systems of record and core systems to the public cloud. And for that, Google is not a great solution because it's actually less performant for certain simple tasks. It's not as secure today. It probably will be secure later on, but as it exists today, it doesn't provide certain functionality, which is key. An example of that security limitation is something called customer managed encryption keys. So Google does not provide it because it's a service. I'm sure Google is going to fix it in the future. But in any case, for the class of problems that we're talking about here, Spanner would not be the right solution. For other systems, it may be.
Okay. Can one transaction engine be mapped to two separate storage engines?
The answer is yes. So this is a very insightful question. Probably a lot of people online will not be able to decipher this, but essentially NoGB is a distributed database, and it's made up of multiple servers, and servers may play one of two roles in the system. It's either transaction processing. These are the servers to which applications connect and process SQL transactions and respond to applications and so forth. And then there's another role called storage manager. That these are the servers which make sure that the data is safely stored on a disk. It's stored somewhere. Those all interact all the time. So there is no predetermined relationship between number of servers which do transaction processing, storage management. But effectively, the normal practice is that you would want to, depending on what kind of systems you have, a bank normally deploys 4 storage managers, and that translates into a replication factor of 4. So effectively, your data is safely stored in 4 different locations at once. And that guarantees pretty good reliability or resilience in case of one or more servers or storage devices fail, right? And those are normally deployed across 2 data centers or 2 availability zones. And then number of transaction engines actually varies, and specific to the size of the transaction processing workload that you're servicing or the system is servicing. So and that's really the tier of the database infrastructure which provides what we would call a scale out, right? And a good example of that, you would do, let's say, close of business day processing, where at the end of the day you have to apply all interest rates, all the balances, and so forth. So how do you do that? The load spikes, and the traditional technology, you need to provide much more capacity to be able to handle that close of business processing capacity. In the case of NoGB, it's much simpler. You size the database to be sufficient for your daily workloads, and then during close of business time, you spin up more transaction engines, and that's what allows you to dynamically address the increase in processing demand on demand, right? And therefore that reduces the overall cost. You don't have to keep this capacity around. You can only bring it up when you're doing certain processing, and then you take it back. And then sort of like going back to the original question, one of the first questions were, how is traditional database different than NoGB in a cloud? And that's exactly this, right? You cannot consume traditional database on demand. It's always there, right? NoGB is different. It's you can consume it proportional to the workload that you need to service, and that's a fundamental difference, which results in, we normally see, at least 10x in terms of TCO reduction by using applications with NuoDB.
A follow-up question to that one was, would the storage and transaction engines work in a hybrid cloud model where the TE is in the cloud and the SE holds sensitive data on-premise?
Yep. So that's, again, very insightful question. We do have a number of customers who actually, for regulatory regulations, so it's redundant, but cannot keep the data, cannot store the data in a public cloud. And then a very simple configuration is to have storage managers and certain transaction engines on premises in a data center, and spin up additional transaction processing capacity in a public cloud for the purpose of either some sort of a spike load processing or other considerations. As long as there is a reliable high bandwidth connection with low latency between the bank, the data center, and the public cloud, NoDB doesn't really care where you execute those servers. They all are viewed as a single logical database, and that's what enables this kind of deployment, in a very straightforward way.
Okay. And the final question today is, lift and shift leaves the benefits of the cloud space untapped. Do you see banking utilizing containers in the face of security and compliance?
Great question. I'm not quite sure how two parts of the questions are connected, but let me try to answer the first one, which I think first is more of a statement rather than the question. Absolutely agree that while one can do lift and shift, it's really not just executing. It's just changing the place the existing system executes in. In terms of containers in general, we haven't touched that, but NoGB now for a number of years we worked very closely with Red Hat as one of the first companies embracing enterprise use of containers. Great partners, very productive relationship where NoGB is really optimized and in terms of features, featureful around container space. So clearly, we see every cloud native application going forward leveraging containers in one form or another. And containers provide additional capabilities in terms of native capabilities, in terms of security and efficiency and so forth. So I'm not sure if I'm answering the question, but NoGB takes full advantage of containers. We're probably on the leading edge of adapting containers for stateful processing. We actually are deploying, just a quick example at the end of the session, right? We are in a process of final weeks and months of deploying a bank in Asia, which operates in containers in a multi-cloud configuration across two clouds. In that case, it's Azure and AWS. So part of the system runs in Azure, part of the bank runs in AWS. The reason for that is regulatory, right? As the banks are allowed in certain Asian countries to put private information, core banking information into the cloud, public cloud. But the requirement is that the data has to reside in at least two clouds, and that's what NoGB delivers. So that implementation is all container-based, and we did have to collaborate quite closely with a number of container provider companies to make sure that you can have clusters across different environments operating in a fashion that allows a database like ours to take advantage of that. So we've done that, and it wasn't easy, but we're very close to actually this particular bank opening the doors for business.
Awesome. Well, thank you, Boris. I think that's all for today. Thanks for the great presentation and demo. Thank you to our audience for attending the session this morning. We hope you found today's webinar informative. Be sure to visit nuodb.com for more information. Thanks again, and see you next time.